Hi, let's talk about momentum. Momentum is inertia in motion. Remember, inertia is the feature of an object that resists changes in motion. So now we're going to look specifically at stopping or changing motion. So momentum is inertia in motion. We learned already when we first learned about inertia that a heavier object is harder to stop and a faster, well, okay, the second one we didn't learn yet, but now we're learning. A faster object is harder to stop. So a heavier object is harder to stop, and so is a faster object. So momentum covers these two ideas. So a heavier object is harder to stop. Okay, that's mass. Mass is how heavy or what something is made of. And then a faster object, well, that would be like speed or velocity. Okay, so this is telling us that mass and velocity or speed, or both, impact the momentum or are related to momentum, which again is changing the motion of an object. So what we find is that momentum is equal to the mass of an object times its velocity. And its velocity here instead of just speed, because direction matters. Momentum is also a vector, so we care about its direction. And here's the equation in variable form. So momentum is given by a lowercase p. I don't actually know why. Maybe I'll take time to look that up for you. But it's a lowercase p for momentum, and then we know mass is in lowercase m and velocity is a lowercase v. So this is just saying the same thing, that momentum is mass times the velocity. So we can look at an example of this. A container ship is a really good example of a heavy object moving slow that has a lot of momentum. So it's really hard to stop a container ship even if it's not going very fast, because it's super massive, and so it has a large momentum. So the mass is big, the velocity is small, but that gives us a big momentum. Impulse is the change, or yeah, changing the momentum. So usually a change in momentum would be a change in velocity. Since the mass doesn't usually change, it can, but it doesn't usually. But if we change the velocity, that means there must be acceleration, because changes in motion, changes in velocity require acceleration. And if there's acceleration, there has to be a net force or a non-zero total force. So impulse is what we call the force times the time interval that changes the momentum. So impulse is a force applied over a period of time that changes the momentum of an object. It's force times the time interval, or impulse is equal to force times time. And impulse is a capital J. That's how it is labeled. So this is just variable form and the equation itself. And so this is force with capital F and time with a lowercase t. And to change the momentum of an object, you want to apply a large force over a short time or a small force over a long time. Depending on the object, though, it might not be a good idea to apply a large force. For example, a large force could destroy an object in the process of slowing it down, while a smaller force over a longer period of time can slowly bring an object to rest. So we're connecting here. Impulse is a force applied over a period of time, but it is also a change in momentum. Okay, so I know this looks a little overwhelming. We'll talk through it. So both sides of this equation here are impulse, right? So this side is force times the time. So that's however long, the force that's applied and for however long it's applied. This side is the change in the momentum. Both of those equal impulse. So we're just putting these two halves of the equation equal to each other. So change in is this little triangle. That means change in, and that means the final minus the initial of something, or like the ending momentum minus the starting momentum, whatever that looks like. And this is just momentum. It's just mass times velocity. So I know that's like an intense looking equation, but I promise it's not, it doesn't contain as much scary information as you might first think. I like this example from the textbook of a truck moving fast. We know it's moving fast because the velocity, or the v, is really big in this figure. If we want to change the momentum of this truck by bringing it to a stop, we have the option of crashing into a pile of hay or a wall. With the hay, we can apply a small force and have it act over a larger amount of time to bring the truck to a rest. But in the other case, with it running into a wall, the truck would come to rest in a really short period of time, but it would require a very large force, and that would destroy the truck. So if we want to gently bring the truck to rest, we want to apply a small force over a longer amount of time. If we want to just quickly bring the truck to a rest, we can apply a big force in a short amount of time. But again, a big force can be really destructive on the object. Okay. This same idea of impulse changing the momentum of an object is why we have these yellow water barrels on the highway. It's to slow a car down with less force over more time, so that it can be slowed or come to a stop without destroying or too much destruction of the vehicle. Remember, a few lectures ago, we talked about the boxer and the punching bag. This time, the boxer is boxing with someone, getting punched himself. So, how he reacts to the punch determines the force he feels. So the fist is coming in with a certain speed, and his face is what brings it to a stop, right? But because the impulse is the force times the time, the boxer can follow the punch with his face to extend the time of the punch, making the force he feels smaller. So this doesn't mean like leaning his face into the punch. It means moving his face with the punch as it goes. So it's also reducing the amount of force applied anyway, and bringing the fist to rest over a longer period of time, requiring less force that his face is also experiencing. Or he can move his face into the punch to reduce the time the force is applied, but he's going to feel a bigger force. Either of those, both options, change the momentum from whatever the initial velocity of the fist is to zero, right? But what's different is the amount of force that the boxer's face is experiencing. And that has to do with the impulse, which is the relationship between the force applied and the time period it's applied over. So again, if we want less force, we need to increase the time over which we're applying the force. But if we want less time, then that means that the force applied is going to be bigger. What about objects that bounce back after colliding with something? What might that mean for the impulse the object experiences? And how would that be different than coming to a stop? Feel free to take a minute and think about this idea. Pause the video if you want. The idea here is that it takes impulse to bring a ball to a stop when striking the floor, and it takes more impulse to get it moving again. So getting an object to bounce actually requires more impulse than getting it to stop. Or also more impulse is imparted on the object when it bounces. The textbook gives a funny example of a flower pot falling on your head. If it falls and breaks on your head, it wouldn't be good. But if it falls and bounces off your head, that is more concerning because it imparted a larger force on your head in order to bounce off. Not really good news for you either way, like don't stand under flower pots. But just something interesting to keep in mind is that when something bounces, that is imparting more impulse. That means more force is applied during the collision. And I just thought also that was an interesting example. Let's talk systems. So systems, how they work is you can't change the momentum of a system from inside the system. A system can really kind of be anything, but generally what we do in physics is we assign or choose a system. So like with the example of an 8-ball and a cue ball hitting each other, a collision, we can choose which of these is our system. So if it's the 8-ball, that's our system. So like these dashed lines are indicating the system. Then the cue ball is imparting a force on our system. It's colliding with our system. But if it's the cue ball instead, that is the system, not the 8-ball, then the 8-ball is the one imparting a force on the cue ball. But if we put them both together as our system, well, then all of the forces are inside our system. And that doesn't change the momentum of the system. And the idea with this is that the change done on one part of a system is canceled out by an equal and opposite change on another part of the system. So when we split this up into two different systems, we see the force acting on different objects, like one acting on the 8-ball, one acting on the cue ball. Those forces are still acting when we make this, like both of these our system. It's just they're inside the system and equal and opposite. So they end up canceling each other out at the system level. And this is important because of this idea that if there are no external forces, then the momentum of the system is conserved. And so what that means is you could figure out the total momentum of the system before a collision and use that to figure out like maybe the final velocities or something like that after the collision. One second, sorry. So let's use this example to find the momentum of each of the balls before the collision and the total momentum. So we have their masses of 0.2 kilograms. And then we have each velocity. So the 8-ball isn't moving at first. So its velocity is 0. And then the cue ball is moving toward the 8-ball at with a velocity of 1.2 meters per second. So give me 1 second and we will do a quick calculation of this. Okay, let's do this. So I just wrote down the information on this page so that we would have it all, and that's not the, oh no, that's okay, actually. So let's say the momentum, which again is P, little p, is equal to the mass times the velocity, mv. So these both have the same mass, and initially the 8-ball doesn't have any velocity. So we'll say the momentum of the 8-ball, which we'll put little p, and then we'll give it a subscript 8 for the 8-ball, is equal to 0. kilograms times meters per second. Forgot the units there. Kilograms times meters per second. And this is before collision. So then we can find it for the cue ball, because that one, and we'll just give it a C for Q, because it's spelled C-U-E, not Q, like the letter Q. Anyway, unimportant. So for this one, we want to plug in the mass and velocity. So the mass is 0.2 kilograms, and the velocity is 1.2 meters per second. Oops. So this gives us a momentum of 0.24 kilogram meters per second. So the cue ball's momentum before the collision is 0.24 kilogram meters per second. And now we can find the total momentum, because we're treating these as a system, right? So the total momentum, which is given by a capital P, just to like show that it's the total before collision, is the momenta, I guess is the plural, of each of them added together. So 0 kilogram meters per second plus 0.24 kilogram meters per second. So like that part wasn't actually necessary. If we're adding 0 to something, we know it's just the something. So 0.24 kilogram meters per second is the total momentum before the collision. And if we say that these two balls are a system, and we just said that the momentum of a system is conserved in a collision, like as long as there is no external force, as long as the things colliding are within the system, that tells us that the momentum before the collision is equal to the momentum after the collision. So we have the total momentum, and then we could use that, for example, to find the final or the velocity of the objects after the collision, for example. We're not going to do that right now, but that is an option. Okay, now I just want to show you some examples of collisions. So look at each of these separately. So let's start with A. This is like our cue ball collision. We have two objects that are the same mass. One of them is at rest, and the other one has an initial velocity toward that object. Then they're going to collide, and what happens is that they'll just, like, the object that had velocity is just pretty much kind of giving their velocity to the other object. So that's realistically what would happen with our cue ball and 8-ball situation, is that they would have just traded. Like the cue ball, once it hits the 8-ball, would come to a rest, and the 8-ball would have the same velocity the cue ball did. This is in B. We have another example where this time the objects are each approaching each other. They collide, and then they just bounce off with the same velocities they had before, but in opposite directions. And then this one here, C, is kind of I think it's called like overcoming or something like that, where one object like both objects are moving in the same direction. One of them has a much smaller velocity than the other. And so the faster object catches up to the other object. And when they collide, that faster object just gives that extra velocity to the slower object. So we can see that, like, because remember, these are velocity vectors, so they tell us how big the velocity is. So we can see that they just traded. Like the green one had this bigger velocity, now the yellowy one has that, and the yellowy one had a smaller velocity, and now the green one has that. And these are all called elastic collisions, because the objects collide but retain their original form. So they'll collide and then they just bounce off, and they're not changed from that process. Let me show you the next one to show like what a change would be. So this is an inelastic collision. And it's not the start of it is not what makes it an elastic collision. We already saw that you can have one object with no velocity and one object with velocity. That part's not what makes it different. What makes it different is that once they collide, they stick together. So our objects end up combined after the collision. That's an inelastic collision. And here's another example of ways that can work is car crashes. So in this one, both objects are moving toward each other, they crash, and then they just end up at rest, and also destroyed in the end. And here's another one of those like overcoming ones where one car is moving slower than the other, and that catches up, and then they collide. And then they collide and stick together. And so with this one, you can tell, because the illustration uses these little lines to indicate the velocity is going in that direction. So you can tell they're still moving in this example, but they're stuck together. Okay, that's all for now. See you in the next one.